Welcome back to the deep dive. Okay, so we've just spent a good amount of time digging into the source material you sent over a really detailed map, actually, of AI data center chips.
Yeah, it's quite the breakdown.
And our mission today is simple. Give you, the listener, a clear guide to where the power and, maybe more importantly, the bottlenecks are in this whole system.
Exactly. Because what the map really highlights for investors is, well, the current AI supercycle, it's maybe less about clever software right now and more about physics.
Physical limits.
Physical limits. So, like, how fast things can actually connect.
Precisely. Speed isn't just chip design anymore. It's hitting real-world barriers, how close you can get memory, how you package it all.
Got it. So we're diving into that today. We'll look at the AI brain, the memory, the packaging, using some simple analogies, hopefully.
Right, like a factory floor in a warehouse.
Yeah, and then we'll connect that tech back to what it means for investing, especially around why things like HBM memory and this advanced packaging are basically setting the pace for everything right now. Let's jump in. So the core is the AI data center server. Think of it as this huge, super specialized computer factory.
Okay, a factory. And what are its main departments?
Fundamentally, three things. Compute, that's the brain power. Memory, the working space or warehouse. And storage, where the long-term data lives. And it's all held together by some seriously advanced packaging.
All right, let's start with compute the brain. The sources talk about a trio here. The big one everyone knows is the GPU, the graphics processing unit, or AI accelerator. In our factory analogy, what's its job?
The GPU is your high-volume assembly line. It's laser-focused on one task. Matrix math. That's the heavy lifting for AI.
How does it do that so fast?
It's got thousands, literally thousands of small cores working in parallel. Think tons of tiny workers all doing the same calculations simultaneously. That's how you train these massive AI models.
Okay, assembly line makes sense, but it doesn't run the whole factory, right? What about the CPU, the central processing unit?
Right. The CPU isn't the main assembly line worker anymore. It's more like the control room or the general manager.
The manager, okay. What's it managing?
It handles the operating system, schedules all the jobs for the GPUs, manages memory access, network traffic. Basically, it orchestrates everything. It's great for tasks that have to happen one after another, sequentially.
Got it. GPU for parallel math, CPU for managing, and there's a third piece, the DPU.
Yes, the DPU data processing unit, or sometimes called a smart NI. This one's often overlooked, but it's critical for efficiency. Think of it as the logistics and security specialist.
Logistics and security, how so?
It takes all the annoying background tasks off the CPU's plate. Things like managing network traffic, encryption, data compression, firewall security, all that stuff.
So it frees up the CPU to focus on managing the GPUs.
Exactly, and it lets the expensive GPUs focus only on doing the AI math they were built for. It really boosts the overall work per watt efficiency of the whole system.
Okay, factory floor covered, GPU assembly line, CPU control room, DPU logistics. Now let's talk about the warehouse, the memory hierarchy. You said this is where the limitations start.
Yeah, this is where physics really bites. At the very top, the premium stuff, is HBM high bandwidth memory.
High bandwidth memory. What makes it special, and why is it so critical?
Okay, picture this.
Yeah.
Instead of memory chips lying flat on a board, HBM stacks them vertically, thin layers of memory one on top of the other.
Stacked. Wow. How do they connect?
Through thousands of tiny vertical tunnels called TSVs through silicon vias, it's incredibly complex to manufacture.
Why go to all that trouble?
Because AI models need to move enormous amounts of data to the GPU, like right now. HBM creates this incredibly wide, incredibly fast data pipe. Think of it as a super fast multi-lane highway or maybe a giant high-speed cargo elevator directly connected to the assembly line.
A cargo elevator. I like that. So if that elevator is slow or too small?
The whole GPU assembly line grinds to a halt. It starves for data. That's a key bottleneck.
Okay, HBM is the premium fast elevator. What about standard memory, like DDR5?
DDR5 is more like the general warehouse floor. It gives you lots of capacity. It's cheaper, but the access speed, the bandwidth, is much lower than HBM. It's the standard working memory, mainly for the CPU.
So HBM for the GPU, DDR5 for the CPU mostly. But what if the AI model is just huge, bigger than the HBM can hold?
That's where CXL comes in, Compute Express Link. Now, CXL isn't memory itself. It's a standard, a high-speed connection.
Like a special highway.
Kind of. Think of it as a very fast, very smart hallway that lets the CPU connect to external boxes of memory or even other processors and treat them almost like they're local. It allows for pooling resources, making the system more flexible for really enormous models.
Interesting. So it helps scale up.
Right.
Okay, final piece. Storage. We usually think of SSDs, solid-state drives. The sources mention the controller inside the SSD. Why focus on that?
Because the controller is the brain of the SSD. The flash chips store the data, sure, but the controller manages everything, where data gets placed, fixing errors, making sure the drive doesn't wear out too quickly.
And why does that matter for AI speed?
Because you need to load massive training data sets and save model checkpoints constantly. A fast GPU is useless if it's sitting idle, waiting for data from a slow SSD. So innovations in controller tech directly impact that real-world data loading speed, feeding the whole AI beast.
Okay, factory built.
Yeah.
GPU assembly, CPU manager, DPU logistics, HBM elevator, DDR5 warehouse, CXL hallways, and fast SSDs managed by smart controllers.
Seems powerful. So, here's the key question for investors. Where are the bottlenecks now? Why isn't this factory running at infinite speed?
Right. And the core insight, the thing you really need to grasp, is that today's main bottleneck isn't really about designing slightly faster logic gates on the chip itself.
No. What is it then?
It's about physical attachment and manufacturing supply.
Yeah.
How close can you physically get that HBM data elevator to the GPU assembly line? And can you even build enough of these complex components?
Back to the HBM. You said it's hard to build. Notoriously hard. Stacking those thin layers perfectly, drilling those thousands of tiny TSV connections without defects. The yields are much lower than standard memory. If one layer in that stack is bad, the whole expensive HBM module might be junk.
Ouch. So low HBM yield directly limits how many fast GPUs can actually be deployed.
Directly. And this is where the other huge bottleneck comes in, advanced packaging. It's the essential glue holding the most critical parts together. Honestly, it's probably the single most important constraint in the investment picture right now.
Advanced packaging. Okay, let's unpack that term. It uses things like 2.5D or 3D stacking. What does that mean physically?
It's all about getting the GPU chip and the HBM stacks extremely close together on a shared base, usually called a substrate or an interposer. 2.5D means they sit side by side on the special interposer base. 3D would mean stacking chips directly on top of each other.
And the goal is?
To make the connections, the data highways between the GPU and HBM as short and as wide as possible. Minimizes delay, maximizes bandwidth, like having that HBM cargo elevator open directly onto the GPU assembly floor.
How do they build these tiny, wide highways on the interposer?
It requires laying down incredibly fine patterns of wiring, and the current gold standard for doing this, especially for these big AI chips, is a technology from TSMC called CoWoS.
CoWoS, what's that stand for?
Chip on wafer on substrate. It's basically TSMC's flagship 2.5D packaging method that puts the GPU die and HBM stacks side by side on a silicon interposer, which then sits on the final package substrate.
And the sources also mention ABF, Ajinomoto buildup film. What's that?
Ah, yes. ABF is a specialized insulating film material. It's crucial for creating those superfine circuit layers on the substrate part of the package, the bit the interposer sits on. Think of it as the special asphalt needed for the ultrafine lanes of the data highway.
So if you can't get enough high-quality ABF film,
You can't build enough of the high-performance substrates needed for CoWoS and similar packaging. It's another potential supply chain choke point rooted in material science.
okay, connecting the dots here for investors. The actual manufacturing capacity for advanced packaging like these CoWoS lines at TSMC, and the supply of key materials like ABF substrates. These things effectively dictate how many complete AI accelerator modules, the GPU plus its HBM, can actually be shipped.
That's the crux of it. It's a back-end manufacturing bottleneck, HBM yield and packaging capacity that's throttling the pace of the entire AI build-out, even if the chip designers have faster designs ready.
And this capacity needs to ramp up fast.
Dramatically fast. Otherwise, the whole AI supercycle stays limited by how quickly these physical components can be made and assembled.
Which leads us perfectly to the investor's view. If the constraint is so physical, where do the sources say we are in the overall AI investment cycle?
The consensus seems pretty clear. We're in the expansion mid-phase. We're past the initial ramp-up. Demand is strong. Shipments are rising. But we haven't hit the peak yet.
And crucially, these bottlenecks are keeping supply tight.
Exactly. Which means the companies controlling those bottlenecks, HBM makers, packaging providers, have significant pricing power. The outlook is generally strong through 2026 because this build-out is such a massive undertaking.
Okay, mid-expansion, constraint-driven. So for investors trying to navigate this, what's the micro-level checklist? What three things should we be laser-focused on?
Right, the three-item investor checklist boils down to tracking the scarcity. Number 1, HBM supply. Keep a very close eye on yields and output from the big memory players, SK Hynix, Samsung, Micron. Is enough HBM actually getting made? It's the lifeblood.
Okay, HBM supply. Number 2.
Packaging capacity. Specifically, CoWoS and similar advanced packaging lines. Are they ramping up production fast enough? Watch reports on monthly output volumes, utilization rates. This is absolutely critical.
And the third item.
Upstream support. You need to look at the companies that enable HBM and packaging production. That means the semiconductor equipment manufacturers, the ones making the tools for drilling, TSVs, for inspection, for lithography, like EUV from ASML, and the inspection side, like KLA. Their orders and guidance are leading indicators for future capacity.
Let me push back slightly here. We hear about NVIDIA, TSMC, Intel pouring billions into expanding CoWoS and similar packaging capacity. Why are we so sure this bottleneck lasts another, say, 2 years? Could the ramp happen faster than expected?
It's a fair question. The investment is huge, absolutely. But building these advanced packaging lines is incredibly complex and has very long lead times. Some of the specialized equipment can take well over a year, maybe even 18 months to order and install.
So it's not like flipping a switch.
Not at all. You're building highly specialized facilities. So while capacity is growing, the sheer physics and logistics of building it out mean the velocity of that ramp is inherently limited. That's why most analysts feel confident scarcity will persist through 2025 and likely into 2026.
Okay, that makes sense. Physical limits on the ramp speed itself. So beyond those specific bottlenecks, what are the broader, maybe easier to track dials for a macro health check on this cycle?
Yeah, the 5 easy dials. These give you the bigger picture. Dial number 1, king metric number 1, HBM shipments. Just track the total volume shipped each quarter. Is it meeting expectations?
Okay, dial 2.
King metric number 2, packaging output. Again, look for reported monthly or quarterly output volumes for CoWoS-like services. Is that number climbing significantly?
Got it. HBM volume, package volume, third.
Equipment guidance, WFE. WFE stands for Worldwide Fab Equipment Spending. Are the forecasts for spending on chip-making tools across the board pointing up consistently for the next couple of years? That signals confidence in future demand.
Fourth dial. Has to be the customer, right?
Exactly. Hyperscaler CapEx. Watch the capital expenditure plans announced by the big cloud providers Google, Amazon, Microsoft, Meta. Are their budgets for building out AI data centers continuing to rise, or are they hinting at a pause? That's your end demand signal.
And the fifth, final dial.
Basic economics. Price and inventory. Keep an eye on spot and contract pricing for DRAM and especially HBM. Are prices stable or rising? Are inventories lean? If prices soften or inventories build, it could signal that supply is starting to catch up, which is the classic sign of a cycle potentially turning.
Okay, 5 dials. HBM shipments, packaging output, WFE guidance, hyperscaler CapEx, and price inventory. Now, thinking about sector performance in this kind of mid-expansion, scarcity-driven phase,
Yeah.
who tends to benefit first?
Well, historically, in a cycle defined by scarcity, the value accrues to whoever owns the scarce resource. So you typically see the memory and HBM leaders like SK Hynix, who's been very strong in HBM, but also Samsung and Micron perform very well early on.
Because they have the bottleneck product.
Precisely. High demand, tight supply equals pricing power and high factory utilization for them. Then you often see the main beneficiary of that output, the GPU leader like NVIDIA, continue to perform strongly alongside the core equipment makers who are enabling the capacity build-out. It aligns perfectly with this whole HBM and packaging story.
It really ties together. So wrapping this part up, the big summary takeaway seems almost too simple, but it's powerful. This current AI supercycle isn't just about cool software or the next chip design tweak.
Not right now, no. It's fundamentally being paced by physical scarcity. Plain and simple. HBM availability and advanced packaging capacity. Those two are the real governors on growth today. They matter more than minor improvements in chip logic speed, at least for the moment.
Which brings us to the final provocative thought for you, our listener. The base case we've discussed, supported by the sources, is this strong, scarcity-driven growth continuing through 2026.
Right. But there's always a but in cycles. What happens if this massive investment in HBM and packaging capacity does succeed, maybe even faster than expected? What if new technologies, maybe true 3D stacking, come online and significantly boost output density?
You could see a scenario where supply actually starts to catch up or even overshoot demand.
It's the inevitable risk towards the end of any big build-out cycle, maybe late 2026, perhaps into 2027. The question for you, as an investor, is when? When will today's bottlenecks, those ultra-fast elevators and assembly lines, become widely available, maybe even abundant?
And how will that shift from scarcity back towards potential oversupply change the entire investment landscape for these stocks?
Exactly. That's the multi-billion-dollar timing question. So keep watching those core metrics. We talked about HBM yields and shipments, packaging output ramps, WFE guidance. They are the speedometers telling you how much road is left in this specific constraint-driven phase of the AI supercycle.